Hello everyone and welcome to this video. Today I'm going to be spending some time to show you how to utilize AI technology to monitor agricultural crop fields. I'll be focusing on two use cases starting from Lebanon and moving to Sudan. Through this workflow, we will learn how to fine-tune a pre-trained Sam LoRa model inside ArcGIS Pro. Let's get started and move to Lebanon. Here we are looking at agriculture crop fields in Lebanon, extracted with the Sam LoRa model that I previously trained on approximately 600 crop labels with a 2-meter resolution. As we've seen, the model has performed with high level of accuracy in Lebanon. Currently, I am facing another challenge, monitoring crop fields in Sudan. I want to take this model for a test ride, yet my expectations aren't very high. I know the model was trained in Lebanon and Sudan got a pretty different geography. Yet, let's take a trip to ArcGIS Pro and see what we can get out of this workflow. I've ran the classified pixels using deep learning geoprocessing tool to classify the agricultural fields in Sudan. For a model that was trained in a different geography, I am impressed with the results. Yet, as you can see, there is some gaps, and I believe with fine-tuning, I should get certainly better results. To improve the results of this model, I'm going to take you through the process of fine-tuning the Sam LoRa model. To do that, let's head back to ArcGIS Pro and kickstart this part of the workflow. As you can see, I will start with two pre-configured feature classes, one for my training data and one for my area of interest. I will label each and every visible agriculture field within the AOI. To not bore you through this process, I will fast forward approximately 25 minutes of labeling exercise. The next step after completing my labeling is verifying the count of labels I've created. I'm going to view that. I've got 206 labels. The next step is really exporting training data for deep learning. I'm going to search for the tool and then open it up. I'm going to use my word imagery as an input raster. Note that this is available in the Living Atlas for global usage. I'm going to then create and assign a folder to save my training data to. Next, I will assign the training data we created in the previous steps and choose the class field, which I've mentioned earlier on. I cleared the selection just to make sure we include all the training data. The next step is utilizing the AOI we've created. So I'll choose that as an input mask polygon and pick up on classified tiles as my metadata format. This is a very essential step for the workflow. To learn more about metadata format, I highly recommend visiting Deep Learning Model Architecture and checking the different models. I'm here highlighting Sam LoRa and its classified tiles metadata format. Back to Pro, I'm going to navigate to my environments and I want to specify cell size of 2. I'm going to show later how to access the MD file and get that number. I've previously trained the model on. Also, I'll specify the extent just in case, but that's really not an essential step as we have AOI. I'll run the tool. This will take a second really as we have minimal training data. The next, I want to examine the exported training data. I'll navigate through my catalog to the training data directory and just drag any random image from the images, then a label from the labels. This will allow us to really examine how the training data looks like and if it's reasonable or not. And as I can see, yeah, indeed, we've got the labels for agriculture fields visible in white, and the image is out there. Up till now, we've learned how to label and export training data with the correct metadata format. In the next step of this video, we will learn how to fine-tune the deep learning model that we were introduced to at the beginning of this video. We will start with exploring the deep learning model that we're going to use. For that, we're going to change a DLPK into a zip, into a safe directory. We're going to then extract the zip file and look for our EMD file in there. We locate the EMD file, open it, and explore the different parameters around our model. The model is an image classification model. It was trained with Sam LoRa, and we can read that in the EMD. We can see the fields from a value and name perspective that it's going to predict. We can learn about the metadata format through the dataset type, that is the classified tiles. We can also learn about the cell size. It says here 5, but we're going to fine tune with 2 meters, which is totally fine for this workflow. Also, we can learn more information as the backbone of Sam LoRa, which is VITB, or Visual Transformers Basic. Back to ArcGIS Pro, we're going to move forward to training the model. I'm going to use the Train Deep Learning Model Geoprocessing tool. We are going to assign our training data as an input data. We're going to also modify the output folder for the model where we're going to save it. Then for the pre-trained model, we're going to navigate to the EMD file that we just exported in the step before to train that model. Take it as the initial model that we're going to train. I updated max epochs to 50 and then left all the other as defaults. As I run the Train Deep Learning Model tool, I'll monitor its messages through the details pane. I'll also bring command line run NVIDIA SMI L5 to monitor the GPU and RAM utilization visible on the screen. As the model completes training, I can see a reported accuracy of 91% based on the data I've given. It's not on any or all crop fields, it's based on this data. The model can predict with 91% accuracy the agricultural fields. Next, we will work on extracting agricultural fields. We will use specified pixels using learning, utilize the input imagery word imagery, rename the output, navigate to the trained agriculture Sam LoRa model. We will then edit the environments and first edit the cell size to 2 meters and work on a small extent for testing. I will run the tool. This might take a second as it's a small AI and I can already see results. My first thought, these are pretty good results and I want to go ahead and test with a larger area. I'll zoom to a larger extent, modify the output. From environments, I will update the extent to reflect the larger AUI. Next, I'll run the tool. I fast forwarded through the workflow as this would take around 30 minutes to run. We can see on the large extent that most of the agricultural fields have been identified with pretty decent accuracy. I will next add the agricultural fields that were identified with the initial Sam LoRa model that was trained in Lebanon, and we can directly see the difference. With 200 features, we've automatically enhanced the results of this model to make it more efficient and accurate, really. I'll group the layers together in order to really compare how the model did with the agricultural fields below from the imagery, and as I can see, it is really reporting with pretty good accuracy. I'm zooming into different areas just to really visually explore the results. As a final step, I'd like to do some QA/QC on the exported data. I'm gonna zoom to layer, and then from my toolbox, I'm gonna expand my post deep learning.pyt script. The QR code for this script will just drop on the screen. But for now, I'm just gonna open it up, use my output raster, which in this use case is defined tuned, pick up the class. In the class, I'm gonna pick agriculture field, and then I'm gonna update the name. Really just adding QA/QC for the quality assurance, quality control. I'll fast forward through the tool, as it might take 2 to 3 minutes. The tool just finished running. We can take a closer look at these features, and at this point we're really looking at polygons. As you can see, these are different polygons that pop up just opened on a second screen. And examine some information. It's an agricultural field, and it got an area of, in this use case, 317,000 square meters approximately. To summarize what we've seen today, we've learned how to label training data, export it, fine-tune a model, and then classify our imagery utilizing that model. I highly recommend that you try the same workflow on agricultural fields, but also don't hesitate to take this and try it on any other features that you see through the imagery. The rule is usually anything that you can spot in 3 seconds, most probably you can train a deep learning model to detect it. Thank you for watching, and see you soon.